Okay, so let's talk about Simulink. So most of you have seen MATLAB by now, and you know that you can do some stuff in MATLAB. You can do all sorts of programming and stuff, and there is an environment in MATLAB called Simulink here. So if you're on the Home tab, click on Simulink, and then you get this window, and this is the simulation environment of MATLAB where you can simulate all sorts of systems and in a pictorial way. So basically, connecting the blocks, wiring the blocks together, and this could be a little bit easier to visualize what's going on instead of just writing the code. And it offers a lot of more advantages. As I'll go through the lecture, I'll try to mention them one by one. So let's start by some example and understand what this environment does, and then, as I said, over time we're going to learn about advantages and what you can do. So the first thing we want to do is we click here on the blank model, and our goal is to solve some problems that you have in some of your courses. Let's say dynamics, statics, or anything like that. Basic physics, math, and we're going to look into those. So the first problem I want to solve, and I have done it, but I want to redo it and mention a few things about it, is the simulation of a pendulum. Okay, so here what you have is a pendulum, and this pendulum has mass m at the end and a rope with length L, and the degree of freedom of this pendulum is going to be the vertical angle, the angle the pendulum makes from the vertical line here. And if there is no torque applied to the pivot, there is no other force, and there is no friction at the torque, based on what you know in dynamics, the equation of motion for this pendulum, it is going to be basically theta double dot is going to be negative g over L times sine of theta. Second order ODE, it is nonlinear, and since it's second order, let's say you have two initial conditions. So let's say you bring the pendulum to some angle, and so let's say the initial angle is just any angle you want, as long as it is not really small. So let's say 45 degrees, or pi over 4. Let me write it in radians. And let's say you release it from rest. So theta dot at 0 is what? 0. Okay? So you bring it to 45-degree angle and release it from rest. Correct? So this is in radians per second, and this is in radians. And the goal is, if you went to your DFQ class, the goal here is to solve from all of this for theta as a function of t. And as I mentioned in class, there is no finite solution with the functions that we know in math up to this day that you can provide here and give you this solution. Okay, so nobody has solved this simple looking ODE up to this very day. Okay, nobody has done it, and it has even been proved that you cannot even do it. So there is no analytical solution here. There is no finite term solution here. The only solution is an infinite series, which of course you have to truncate it at some point. You cannot keep going with this series forever, and so you're going to have some approximation, not exact solution. Okay. So that's one way, or you can do it numerically, which again is not going to be perfect. It has some approximations to it, but that's what they do in many applications in engineering, is they try to resort to numerical solutions. So instead of having an actual function, what you are going to have is the values of theta at specific time points. So instead of an actual function, you are going to have basically a bunch of points. And then what you will do is you, in MATLAB or any other software, you connect these points together using lines or any other kind of curve fitting, and then what? You show something that mimics the solution. So it doesn't mean you found this curve, no, you just found the values of the solution at the specific points and now trying to connect them to show kind of like an underlying function. So this is what we are going to do, solving this ODE numerically. And in literature, there are so many different ways to do it. The simplest method that I mentioned in class for you was called the Euler method, if you remember that, correct? So that's one of the simplest numerical solutions for any ODE, specifically of order 1. And the other one that MATLAB uses and Simulink uses for specific category of differential equations, which are called non-stiff equations, is called Runge-Kutta fourth order. Which is more accurate than this guy. So this is what Simulink and the command ODE45 in MATLAB are using for the category of differential equations we call non-stiff. So here, if we want to do it in MATLAB using Simulink, not ODE45, what we need to do is to create some blocks and basically recreate this equation using blocks, implement these initial conditions, and then let Simulink solve it, and then we can look at the solution in an oscilloscope block. Okay, so what we do here is we go to this library browser, and then here under Simulink you have a bunch of different tabs, branches, that each one has tons of different blocks. I'll try to cover some of them. And again, also under this window on the left, there are specialized toolboxes, right? For example, there is a specialized toolbox for aerospace, for computer vision, for machine learning, for digital signal processing, for communications, for you name it, robotics, navigations, for audio systems, for all sorts of things. Some of them are not here, you have to buy them. For image acquisition, there are even for biology and some other things, economics. Okay, but these are all specialized toolboxes with the specialized blocks. This Simulink one on the top, these are the blocks that you can use for many of these applications. So they are generic, kind of general type of blocks, and most of the ones that you use in many of the simulations are under commonly used blocks. So what I need here is to create this signal double dot, theta double dot, and then integrate it twice to get what? To theta. So the first thing I need to do is to do integration. And if I go here, I have this integrator, so I can right click and add it to my blank model, right? Which should come here. And then, let's see. Oh, there we go. So this is my integrator block. And now if I want, I can add one more of this because I need to integrate twice. So I can either Control C, Control V it, or hold down Control and drag and release it. And this operation is going to let me create another one. Okay. So again, if you want to copy a block, you don't need to go back to the browser and bring one more. You hold down Control and then what? Drag and release, right? You see, I can get one more. And if it asks for paste, you say paste. So here I just need two of them. So this signal that is coming in is going to be theta double dot. You integrate it and it makes it theta dot. Theta dot goes to the next integrator and becomes theta, right? And then theta you can connect it to an oscilloscope. So if you go back to the library, under sinks, these are different types of outputs. You bring the oscilloscope block and connect theta to it. So this signal is going to be theta. If you want, you can double click on any wire and write the name for it. So double click here and then type in theta, or double click here and type in theta dot. Okay, so you can give names to the signals. This is theta. You can call it dots dot or double dot, or I call it two dots, theta two dot, theta double dot. Okay, now the question is, what is theta double dot itself? Well, based on what we know, it is a constant, because L is the length of the pendulum, which is a constant. G is a constant, so it's a constant number with a negative sign times what? Sine of theta. So first, I have theta in my simulation. I need to convert it into sine of theta, and then I need to multiply it by a constant number, right? So first thing is, this is theta. Is there any way I can take a sine out of this? And yes, you need to go under library browser, go under math operations. Here there are all sorts of different math operations, and the one we need for trigonometry functions is this guy called trigonometry function block. So we bring it here, and now the goal is to connect that theta to the sine. The output is going to be sine of theta. Now you see the input of this block is on the left, the output is on the right. So if I want, I can just wire this back to theta, right? And then bring this output here to multiply it by again and make theta double dot. Or what I can do is, it's easier if this block was backwards. I mean, the input was on the right and the flipped basically, and the output was on the left. And if you want to invert a block, use Control-I from the keyboard and it inverts it. Sometimes it's better that you rotate a block by 90 degrees. If you want to rotate the block, you just use Control-R. And each time it is going to rotate it 90 degrees clockwise. Okay? So right now, we want it in this situation. So here we go. We get theta. And now, so this signal is going to be what? Of course, it is going to be sine of theta. And now I need to multiply it by a constant number. Anytime you want to multiply any signal by a constant number, you bring a gain block, which is under commonly used blocks. That's this block here, gain. And you see here, I would rather invert this block. So I use Control-I and invert it. And now this gain for me, if I multiply it, it should be theta double dots. Okay? So now what is this gain? Clearly this gain has to be what? Negative G over L. And how much is it? So in this case, negative G, which is 9.81, divided by L. So you decide how long. Let's say the pendulum is what? Half a meter. So here we go, right? And my system is ready to go. Except for what? For initial conditions. I need to plug in these two initial conditions. Theta dot at 0 is 0, theta is pi over 4. So the initial conditions go to the integrator blocks. If you see this guy, the output of it is theta. So if you double click here, when it asks for initial condition, this is initial condition for theta, and it was what? Pi over 4. By the way, if something is like pi over 4 or a bunch of numbers multiplied, divided, or anything, you do not need to go in a calculator and first calculate pi over 4 and then copy this number and what? Come here and paste it here. You don't need to. MATLAB, wherever asks you for something, it has the built-in calculator. So if it's like 2 times 5 divided by 3.6 and then raise the whole thing to the power 3, you can just leave it like this. You do not need to simplify it first, get it into one single decimal and then paste it here. You do not need to. So in this case, you simply say what? Pi over 4. MATLAB will calculate that. Now this guy, the output is theta dots, so the initial condition is theta dot at 0, which in this case is also what? 0, so you leave it as is. And then you can simulate this for as many seconds as you want. Here, let's say I want to simulate it for 10 seconds, so all good. I save this first, and I call it, let's say, nonlinear pendulum or anything. Okay, and then you can, here, so nonlinear pendulum. And it is going to be saved as .slx, a Simulink file. So here we go, we save it. And now we are going to click on the run, and it is going to run it and give me the result that I can see in the oscilloscope. Okay. Now here I have so many other things running in the background, and the computer has not been turned off for some time. That's why you see it's a little bit slow. But typically Simulink is very fast. Okay, and now we can double click on the scope block and see theta versus t at those specific points that are connected by some curves. Okay, so it didn't seem like it ran. Let me run it. You can, by the way, from the oscilloscope block, you can click on the run and run it from here. Okay, you don't need to necessarily run it from directly in Simulink. You can run it from inside the scope block, and there we go. That's the solution, which is we call quasi-periodic. It's not perfectly periodic. And this solution, if you look, it's not quite smooth and nice. It's quite jagged. The reason is the number of points used in this simulation is not big enough. So you are connecting a bunch of points that are quite distant from each other using lines, and that's why you have this jagged behavior. But if you have a lot more points, you're going to see a lot smoother curve. How can you change that? Well, you go here under this gear for the scope block and change the sample time from -1, which means inherited from previous blocks, to something that you want, let's say 0.01. Okay, so in 10 seconds you're going to have about 1,000 data points, and that will make this a lot smoother. So I okay that and I run it again. Again, I can run it from here, and this time I should get a lot nicer curve. There we go. Okay, so this is my solution, again, numerical solution for angle of the pendulum. Now, let's take it to the next steps, okay? So what else can we do here? So we made something. Now we have the results, and it shows it in a scope block, but there are so many other things you can do. If you want to zoom into a specific area, you can what? Click on zoom in, or if you want to zoom out, you can zoom out. If you want to pan, right? So you can do pan. So there are so many things you can do to basically move around. So zoom in, zoom out. If you want to scale basically the x-axis to the limits, or all axis to their limits, you can use any of these guys. So they give you a better view. And if you want to do measurements in any specific point or in a specific time slot in here, you can click on this guy, okay, cursor measurements. If you do that, then it will give you a range between two cursor points, and then you can get them as close as you want, or you can separate them. So right now you see I have a window, and the first point is basically at 2.5, the second one is 7.5, and the values at 2.5 is -0.27, and at 70.75 is basically 0.68. Okay, and now if you want, you can basically grab these guys and bring them closer. So the only thing is, make sure this is not on pan, right? So let me go back to normal view, and let me turn it off, and now I should be able to drag them anywhere I want. Let's say I want to measure the value at about what, 4 seconds. So I bring this very, very close to 4 seconds. Right? And you see here, I can get very close to 4 seconds. Even I can get this guy very close to 4 seconds. Right? And you see this one is even closer. Right? 4.02, and the value is about negative 0.18. So I can get the values in any window that I desire and at the specific points. Okay, so this cursor measurement is a good thing. Not only I can do that, I can also do some other things for the scope block. So let me show you. So here, if I go back to the scope block, let's say if I want to print this, the background is black and it is going to use a ton of cartridge ink if you want to print this background of black and the curve of yellow. So can I change the color of the background or the color of this curve like we do in plot command in MATLAB? Yes. You need to here come under this gear, and then here you have the style and color. Okay, so if you click on the style, it allows you to change some colors. Like what? The color here is the access color. So instead of black, let's say I want to make it white so it doesn't waste my cartridge. And the line, that is this line here, the color is yellow. Let's say I want to make it what, red, and then instead of 0.75 pixels width of the line, I want to make it 2 pixels. So if I say apply, there we go. And if I want to see at which points I have actual data, right, then I can add a marker. So let's say I want a circle anywhere that there is a data point. And then you can see all of those places that you have a data point. You see a circle, and you see the circles are all connected by what? By lines. And you can see that using zoom, right? Here. So you see, that's the base of numerical solution, a bunch of points that are connected by lines, okay? And now this is going to be way better to print. If you don't want this basically surroundings, right? The very edges of the picture, the figure that have basically numbers and everything, you can change the color of that as well. So here, that's the figure color, and you can change that also to white if you want. And now probably this is way better for printing. Okay, now sometimes you might have more than one curve, right? Let's say in this case, not only you want to see theta, you also want to see theta dot on the same oscilloscope. So then if you double click here and go to that gear, then you change the number of input ports from 1 to 2 because you have 2 values to enter, and now you see here you got 1. So now I'm gonna connect this to theta dot. So now I can get both of these guys into this, and now I save and run. And look now. Now I should have 2 curves. If you see, one of them is this thin curve here, and I can zoom in to see that. The bigger curve is theta dot. And if I want, I can change the thickness of it. I can change the color of it or everything. Just I need to go again back under the style and say here, you have 2 theta now. One of them is theta, the other one is what? Theta dot. And I say change the color of that to green. And change the pixel also to 2 and give it a marker of, let's say, what, square. Apply. So now you got your theta dot and theta, and to know which one is which, you can insert a legend. So if you go back here, and then if you go under display, then it says what? Show a legend. So now if you apply it, then you should have a legend on the top right corner. There we go. Okay, so now it is way better. Now, what else can you do here? Well, one other thing you can do is if you have more than one figure, so you want to make like a subplot, right? Like MATLAB, you have several plots in the same figure. We call them subplots. If you want, you can do that. So here you can have a layout, and let's say I want a 2x2 subplot. So all you need is to highlight these 4, and now it is going to convert it into a 2x2 set of pictures. And then each one of them will be separate. Now here in this case, you only had 2 graphs, and let's say here I put them side by side. If I want, you see the problem is here only 2 of them shows as blue. Why? Because you only have 2 signals. If you have 4 signals, then you can have in 4 windows. So the reason you see 2 of them as gray is because you do not have enough signals to show on 4 windows. Okay, but again, you can do subplots if you have enough of signal to show, right? If you have enough of input ports for oscilloscopes, you can put each one of them on one of these windows and have a different layout. So for now, let's just put back everything to one window. Okay, what else can you do? So here, under the time, you're good. I don't recommend you change anything like that. And if you want, you can show labels. Okay. And here you can see that it shows the time axis label, and it says this is time, right? And then you can have grid, or you can get rid of the grid. And if you want, you can change the limits of the axis, right? So here you can make it just -4 to 4. You can provide some value for Y label if you want. Okay, here, right? And if you want, you can also save this data to the workspace. Because when I run Simulink, nothing is going to shown to the workspace except for this out. Okay, and we'll talk about this out. Okay, if you look at this out is not really showing any of the theta or theta dot values here. Okay, but if I want, I can save the data of the scope block to the workspace of MATLAB. So if you want to do better plotting options in MATLAB, I can do it, because Simulink has its own workspace and MATLAB separately, but they can be connected together. I mean, like, for example, let me show you one thing here, and then I'll go back to exporting data to the workspace. Let's say, remember L, I said the length of the pendulum is what? 1/2 meter. So I type in L equal 1/2 here, not in Simulink, in MATLAB. And now I go back to Simulink, and here, instead of saying -G over L and type the values of G and L, I leave L as a parameter. And I OK that. Okay? Now what happens is, here you don't have the value of L typed, but when Simulink cannot find the value of that parameter L, the next place it goes and looks for L is in what? In MATLAB workspace. It says, hey, MATLAB workspace, do you have L? And it says, yes, it's this number. So it reads the L from there. Okay, so here you should not get any problem. It should just work fine because it reads L from the MATLAB workspace. Okay, so you can read data from MATLAB workspace. Now, can you write data to the MATLAB workspace? Sure. One way is through the scope block. Okay. Now here, this is what I'm gonna do. Instead of having this guy 2 input ports, I want to make it just 1 input port. Okay, but I go to the logging and say log the data to workspace for me. Do not limit the number of data that you save to the workspace. Call that variable theta, and the format of it, you can make it a structure with time, data set, and array. I always prefer to work with array, so I leave it as array. and I OK that, and I get out. So now the signal getting out of here is going to be saved as a vector called theta to the workspace. And if I want also theta dot, I bring another one of this guy and send theta dot separately. Now, can I have them both with one scope sent to the workspace? Sure, but I want to show you something different here. So I go here and just change the name of this guy because I just copied and pasted. So I need to make sure I change the name of this to something meaningful. So theta dot, everything else should be the same as the previous one. Okay, so now this one will send theta dot out, and this one will send what? Theta out. Okay, yes? Now, let's run. So now not only you can click on the scope block and see those things, if you go to Workspace, you should also be able to see the values of those variables in the Workspace, and so you should be able to do the plot separately in MATLAB. Okay, so clearly you see the data is there. Now look, I go back to my Workspace. Now again, I don't see theta and theta dot, which is kind of weird, right? Because I expected to have a variable theta and a variable theta dot, two arrays showing up here, but they don't. But if I look at this out variable, now you see it has inside it theta and theta dot. Okay, so if I want to access them, it combined all of the outputs of Simulink into what? Into a structure. So if I want to look at theta, I can say now theta, let's call it T, for example, is equal to out dot theta. Okay? The field called theta from the structure called out, that is the array called theta. And look here, what is T now? That's 1001 by 2 double. Why does it have two columns? Because the first column of that are the time points for each, the T values for each point, and the second column are what? The theta values for each point, right? So each array that Simulink sends to the Workspace has two columns. How many rows? The sample time was 0.01. The total simulation time was 10. So 10 divided by 0.01, that's 1,000, and then plus 1, which is the initial point. So 1,001 data points times 2. So now if I want to plot it, I say plot what? T of column 1, which is the time values, versus what? T of column 2, which are the actual theta values. And I should get the same graph as the scope does. And now I can do all sorts of things that I know with the command plot, right? So that's what I can do. Or if I want the theta dots, then I can say, for example, T out, or whatever you want to call it, T dot is this guy. Out, the field called theta dot. And now I can plot that as well, right? So right, so this is theta dot, and if I want, then I can say hold on. And then on the top of that, I can plot T, but using a different color. Let's see here. And then I can use a legend and say the first one was theta dot, and the second one is theta. Right, and I get something similar to that scope block, as you can see. Right, add X label, Y label, title, and so on and so forth. So I can reproduce everything here, but I can do a lot more, like animation and all sorts of other things. Okay, so far, you can see I can communicate with the Workspace, sending data from Simulink to Workspace and reading from Workspace into Simulink, right? And let me show you one more thing. So let's say you have a program, and this program, you want to run this guy here, this code, this Simulink, several times, each time for a different value of L. You want to change the length of the pendulum, and each time you export the theta data to the Workspace, and then what? plot it, correct? So it says plot the response of a pendulum for 3 or 10 different values of L and see what's the effect of L, right? How can I do that? Well, I'm not going to come each time, change the number L here, run it, save it to the workspace, plot, and then use hold on, rechange, redo, replot, and it's going to take forever. Can I do it using a for loop in MATLAB? Sure. What I need is I go here and create a script, and in that script I provide a bunch of numbers for L. So I say like length is equal to what? From 0.5 with increment of 0.25 to 2. Okay, so I change the length from half a meter to 2 meters with increments of 0.25. And then now I say for I equal 1 to length of length. Now that's not a good naming, so let me use LNG. Each time L is equal to what? That LNG index II. Now that you know the value of L, what would you do? Run the Simulink for me. So it's like here, I went inside the Simulink and changed the value of L. Now that I changed the value, it's time to click on run. Can I run this guy from outside in a MATLAB script? Sure. All I need is to use the command sim. So I say sim, and then inside it, I just provide the name of that Simulink file. That's all it is. So that guy was called what? nlp.slx, right? So I go here and say nlp.slx, and that's it. This is like clicking on the run. And when it does, it sends the data to the workspace. So I should get this structure out, and then I should be able to access the field in it called theta. Now you might wonder, is there a way that it doesn't send the output of the Simulink as a structure? Can it just directly save an array to the workspace called theta? Is that possible? And the answer is yes. But you need to do something. What you need to do is come back to Simulink, go under modeling and go to the model setting. And then on the left side that you see data input, import, out, export. Okay, here. This guy, that's a single simulation output. Call it out. You uncheck this. This way, it's not going to combine all output variables into one structure. It's going to save them each separately as a vector. Okay, so I okay that. So now look, if I go back and run it, here we go. You see? Now you have what? You have the variable theta, right? Let me clear it all and do it again. Okay. For some reason, my MATLAB is running slow today, but it should be fine. There we go. Here. And now you should be able to see theta comes out that you can directly use. Okay, so you don't need to access the fields of a structure here. Oh, come on. Oh, L. It needs L. Okay, let's do it. There is something wrong. Shouldn't be that taking that long. And now you should be getting your L. There we go. So now you see directly theta here, and you can use it. So what you do is here, you say run it each time, then go ahead and plot for me theta of column 1 versus theta of column 2, okay? And you give it a color, a different color each time. So you say color, and here, since you don't know how many times in general you want to run this, and you cannot use the same thing. If you say R, for example, every time it's gonna color the new set of data in red. So in order to make the color of one plot against others different, what I recommend is to use a random color, and I would use rand of 3 and 1. What it does, it generates 3 random numbers and uses one for red, one for green, one for blue of the color, right? And this way you're gonna have random, and then you got this, and you need to hold on so that it doesn't overwrite the previous one. And whenever you're done with this data, if you want, you can clear, let's say, theta, so that the theta that was written from the previous run of Simulink is cleaned, so that the next data comes and replaces that. Although it will be overwritten in general, but I think it's a good idea to clean and rewrite. And here, if you say end and run this guy, so I call it test, and run it, it should run that Simulink file a bunch of times here, I guess 7 times here, and gives you a plot with 7 curves, each one with a random color on it. Okay, so it is now running that Simulink 7 times behind the scene. Okay, and it should generate you the plots. So you're not gonna type the value of L each time, export the data by running the Simulink and doing so. Here we go. You got your data. You got 7 different curves, and you can insert a legend. The only thing is you do not know which one is which. Okay, you don't know which one is for L of 0.5, which one is for L of, although here it tells you this is data 1, data 2. So data 1 is for what? If you want, you can click on this guy and go double click here into the legend and say, hey, this was for L of 0.5, right? And then go here and change this one, say this is for L of 0.75, and go all the way down to the last one and say this one is for L of 2. Okay, and clearly you see that as the length gets bigger and bigger, right? As you can see, your frequency is dropping. Okay? It takes more time for it to do one oscillation, and therefore it is going to have a lower frequency. Okay, so you can also have this text here generated into that code automatically as well, so you don't need to go and do that even manually. So if I want, I can do that, but we'll keep that for another time, because that's MATLAB, not Simulink. So anyways, these are some very basic things so far that I have shown you how to communicate with Simulink directly from an M file and do anything that you want, right? So now let me show you some other things. So what else? So as I told you, there are tons of different blocks here, and each one has its own application. So here I'll try to show you some different things in Simulink. Now note that this video I'm making is not going to be like your ultimate Simulink reference. It's just to get you started on this important tool. So what I will do here, I'm going to make a new file, and we're going to do a different problem. Okay, so like what, for example? Well, I want to show you the use of some blocks and for something important. So let's say here I want to look at the projectile problem. right? So the projectile problem, the governing equations for it, if there is no air drag, is x dot equal 0 and y double dot, x double dot is 0, y double dot is negative g, right? When this projectile is moving in the air, if you don't consider the effect of the air, so it is going with velocity v and with angle theta in general at arbitrary point in the air, and let's say this is your x and y coordinates, the only force acting on it is going to be mg in the negative y direction. That's why you have negative g for y acceleration. Now if you add air drag, the equations are going to be a little bit more difficult, highly nonlinear, and there is no way to solve them analytically, so you have to do numerical. What is it? Let's say I have air drag. When you have air drag, now you have a force in the opposite direction of the velocity, like friction, right? It's very similar in behavior to a friction in terms of being opposite to the direction of motion. So this air drag is backwards, and so if this angle is theta, now your x double dot and y double dot are not going to be that simple. So here you have fd cosine of theta in the negative x direction. So this is going to be negative fd times cosine theta divided by m. And this is going to be negative g and negative fd sine theta divided by m. Okay, because fd sine component is going to be added to mg. Okay, so now these are your equations, and the thing is theta and fd are functions of x, y, and the dot terms, or all of them are functions of the dot terms. Like what? Fd, the drag force, is equal to 1/2 rho of the medium. In this case, let's say it's air, so rho of the air. A is the cross section of the part that is in front of the upcoming fluid, okay, right, exposed to the effect of air. Now if it's like a ball, then this is going to be a circle, times a constant called drag coefficient. This depends on the shape. For a ball, it's about 0.47. It's not really constant. It does depend on the speed of the projectile, but for the moment, to make life easy, let's say this is just a constant number, and then times magnitude of the projectile squared. So if you look for simple considerations, you can say this cross section of the ball is constant, drag coefficient constant, rho of air constant. Of course, none of them is really constant. This changes with the angle theta. Okay, unless it's a ball, then yes, it is constant really. But any other shape than ball, this A would change as the angle between the ball and the stream would change. CD does depend on V, and rho depends on the elevation. So for the moment being, let's make life easy. Let's say this whole thing is just a constant C. But the problem is V squared is what? It's x dot squared plus y dot squared. And the angle theta itself here, the angle theta, tangent of theta is what? If you can see, it's the Vy component over the Vx component. So it is y dot over what? X dot. Therefore, the theta itself is tangent inverse of y dot over x dot. So if you go back to these equations of motion, they're going to be like x double dot is negative that constant c over m, that's another constant, times what? X dot squared plus y dot squared times cosine of tangent inverse of y dot over x dot. And y double dot is negative g minus c over m times, again, x dot squared plus y dot squared sine of tangent inverse. So clearly you see that your equations of motion are second order. They are coupled. In X you have Y, in Y you have X, and they are highly nonlinear. So there is no way you can solve this analytically. And here, since you have 2 second-order ODEs, then you need 4 initial conditions. So you need to know X at 0, how much it is. You need to know Y at 0, how much it is. And you also need to know what is X dot at time 0 and what is what? Y dot at time 0. You need to know these 4 values, and then you can simulate the behavior of what? This drag, right? This just comes from the drag. Now, how do I do it? I'll show you. So I go back to the library. Now what I need here, I need the gain block, I need the constant block, I need to add some stuff together, so I need the summer block. Then I need to integrate, so I need the integrator block. I need the trigonometry function, so I go under math operation and bring it. Then I need to square something, so I can bring in the square function, which is not a specific function here, but you can get it under math function. And then I need some way to show X versus Y, right? Because I don't want to show X versus T or Y versus T. I want to show X versus Y, and that is under sinks, and that is called XY graph. By the way, since the simulation keeps going until we stop it, it might hit the ground and keep going under the ground, although it cannot happen in real life. So I need to have a mechanism to stop the simulation once the projectile hits the ground. And for that, I need the stop simulation block, and I also need a comparison, which you can find under logic, okay? And that will help me run this whole thing. So I need 4 integrators, 2 for X double dot and 2 for Y double dot. So let's make 4 of these. Now, if you look here, this is another constant. This is another constant, so we can call it K. And then we can simulate this motion. Now let me provide some numbers here. So let's say X at 0 is 0, Y at 0 is 20 meters. And then X dot at 0 is going to be the launch velocity times cosine of the launch angle. And let's say the launch velocity, and this is the launch velocity times sine of the launch angle. Okay, and let's say here the launch angle is, just you tell me, let's say, 30 degrees. And the launch velocity is, let's say, 100 meters per second. And then we need to calculate the value of K as well, okay? Where K, if you remember, this constant K was 1/2 rho of air times CD times A divided by M. Okay, so we need that, and we're going to come up with a number for this so that we can do a realistic simulation. So here I have plugged in some numbers. So here assume that the projectile is about 50 grams, okay, or 0.05 kilogram. The density of the air at the normal condition, like 20 degrees Celsius, and sea level is about 1.2 kilogram per meter cube. CD for a sphere is 0.47, and let's say the radius of the steel ball or whatever ball it is, the projectile is 5 centimeters, so the area is going to be 25 pi times 10 to the negative 4. If you plug in all these numbers, constant K is going to be 0.0443, okay? So now with that K and with this governing equations that we had, we are going to simulate the behavior of the projectile until it hits the ground. Okay, so let's go ahead and do it. So x double dot is negative drag force divided by m times cosine of theta. Y double dot is negative g, which is a constant, times negative drag force sine theta divided by m, and then we have some initial conditions. So what we need here is, let's say this signal is x double dot. Okay, so I call it x2 dot, and then here is x dot. You integrate it, and then you have x, and then similarly this is gonna be y, and this is gonna be y dot, and this is gonna be y double dot. Okay, now your x double dot is drag force times cosine theta. Okay, so I need sine and cosine, and I also need arctangent to make theta. So I change this guy to tangent inverse, and I change this guy to cosine, and then I need a gain that is k, and that k for us is 0.0443, right? Okay, so I got gain k, and my y double dot is two numbers, both negative. So here I need two negative numbers. One of them is constant. That constant is negative g. And the other one is negative drag force divided by m times sine theta. So if you want, or you can do both of them negative and then keep this guy as positive. And so I need to divide y dot by x dot to get arctangent. So first I need to divide two signals, and to divide two signals I need to go to math operation and bring the divide. Okay, so this guy, if you pass to it, the numerator goes to this product, and the denominator goes to the divide. So this guy is going to be y dot divided by x dot, and if you bring it here and take arctangent of it, this guy here is going to be your theta. So this thing comes out is theta. And now you need also the drag force. So for that you need to square both x dot and y dot. So you bring this math function and change it to a square function. Okay, and you invert it. And now here you need to square both x dot and y dot. So if you want, you can basically have two of that, like this. One of them you attach to y dot, one of them you attach to x dot. So now they're squared. Now you need another sum block here, where you add two signals together. So this is x dot squared plus y dot squared. So this guy is v squared. And then you have theta. And if you multiply v squared by this constant k, This is gonna be your drag force divided by m, which now needs to be multiplied by sine and cosine of theta. Okay, so you need to bring these guys both and attach them both to theta. Okay. So this is sine of theta. Then you have cosine of theta. And now this signal that is drag force divided by m should be multiplied by them. So you need to multiply two signals, and for that you can go under commonly used blocks and bring the product. Here I do Control R to rotate it, and I need two of this guy. So one of them is going to be sine theta, one of them is going to be cosine theta, and both of them are going to be multiplied by this drag force, which is divided by m. Okay, so this guy, as I said, is drag force divided by m. And so now the sine term will go here, and the cosine term is going to go there. Just it should be negated, right? Because it's negative of that. So what I need is a gain block here, and this gain block is simply -1 because I have negative ft cosine theta. Okay, so now I guess my equations are all right. The only thing is initial condition. So this is x dot at time 0, and it is going to be v launch velocity times sine of or cosine of the launch angle. And then y dot is going to be again the launch velocity times sine of the launch angle. Then we have x of 0, which is 0, and then we have y of 0, which I guess we consider like, make sure 0 to any. We consider it to be to any. Okay, and this is good to go. And it's gonna plot x versus y. Now the only thing is, when you do it, it is gonna go as long as for 10 seconds. Now during the 10 seconds, is that gonna hit the ground? Is it not gonna hit the ground? Is it gonna hit and continue? Let's first find out, and then I'll talk about this stop block. So here, let me run it first and look at this XY graph. Okay, so first thing first is you don't see really much here or anything here, to be honest. So first thing is you need to double click on this and change your limits. Okay, right now it's just between -1 to 1, and you have a small sample, inherited sample time. So I make it small so that the plot of it is smooth. Y max, I make it a little bit big for now. And X max is something like that as well, and 0. Now run it again. There we go. Okay, so clearly you see the motion, and the projectile is not going to be a parabola anymore. It's a skewed parabola, and as you can see here, when it hits the ground here and y becomes 0, it keeps going. So right now at this point x is about 60 something, but y is negative, and it cannot happen. Y negative means below the ground. So you have to stop the simulation when y becomes 0 or negative. You have to stop it. So to do that, you're going to compare y against 0 and say, hey, is y against 0? Is y is less than 0? If it is, then what? Stop the simulation. So whenever y becomes 0, it's not going to go 10 seconds. Whatever time it is, it's going to stop it right there. Okay? So that's like an if condition. And there we go. You see? Right here, when it hits the ground, you're going to stop it. And there we go. This is a very good show of the projectile motion, XY graph, right? So this is another example of a real problem done in Simulink and a lot more blocks. Now let me show you a couple of other blocks that you see under commonly used, and they are quite useful. One of them is mux and demux. This is when you want to combine several signals into one signal, and here is when you want that combined signal to go back into individual signals, okay? Many times these are useful when you are working with systems of multiple inputs, multiple outputs. So you want to combine signals together. It's like, for example, behind your TV, you have a bunch of cables, and you don't want all cables to be laying around. You're going to put them all in a sheath or in a one of these covers that are on the wall, and you kind of hide them. But again, when they reach behind the TV, you want to bring them out of that sheath, right, or that cover, and then put each one of them to their corresponding plug-in. So this is the work of mux and demux, or multiplexer and demultiplexer. So if you want, you can bring one of these, and I'll show you in this example how we can use it. So here, you see, I brought X dot and Y dot and raised them to power 2 separately because they were two different signals. Now, one thing I can do here is, if you want, what I can do is I combine these two signals into one signal using the multiplexer. Okay, so here I bring these signals into the multiplexer, make them one signal, raise that signal to power 2 one time, so I need just one of these. Okay, just one of them. So now the output of this is one signal, but it has two elements, X dot in it and Y dot, right? Now the signal has two parts in it, X dot squared and Y dot squared. Now I can separate them and then add them together. So what I need here is now the single signal that is coming out. Now I'm gonna put it back into the components that it had. So now this is going to be X dot squared. This is going to be what? Y dot squared, right? But I could combine them before raising them to power 2. So I use one of these blocks instead of two. And now I separate them and square them. And so this should give you the same result. There we go. Okay, so multiplexer and demultiplexer are two useful blocks here.